Right, in this video and then the next one, we're going to look at some reactions that are similar to ones that we saw in our last unit, and we're going to be looking at addition reactions to alkynes. And in some ways, these are going to be similar to the reactions we saw with alkenes. So let's just start with, for example, the addition of HX. If we have a terminal alkyne, we can follow Markovnikov's rule by adding a hydrogen to the least substituted carbon, and the halogen goes to the other one, just like if it were an alkene. Now, the big difference is we're only getting rid of one pi bond, so we still have an alkene. So there's two hydrogens on this carbon, and the halogen is over here. So again, we're following Markovnikov's rule. Now, what's interesting about this is if we regulate the stoichiometry, if we use an excess of HX, it will add multiple times. So you'll get two halogens on one carbon and an additional two hydrogens on the other carbon. Let's think about how that happens. It's kind of a back-to-back step series of the same reaction. 1 mole of HCl will add to do the first Markovnikov's addition. And now we're kind of in our last unit, that territory, because the next one will add, again, following Markovnikov's rule. So the stoichiometry really plays a role, and you have to look at that in the in your reaction. So in your homework on exams, how do you know if you're supposed to add only one or if you're supposed to add two? The reaction conditions will tell you. If it just has this, no stoichiometry with it, you assume you're only adding one. If it says excess, or sometimes you might see like 2 HCl, then you know you're supposed to add it multiple times until you're out of pi bonds. Now, if there's a way to do this to do a Markovnikov's addition, can we do a non-Markovnikov's or anti-Markovnikov's addition? We do the same thing as we did in the last unit. We use HX, but we add peroxides to now turn it into a radical mechanism. And so now the halogen goes to the less substituted carbon. And we do typically end up with a mixture of cis and trans. But if we, again, add an excess of HBr, we're going to do that addition twice. So you'll have two hydrogens on the more substituted carbon and two bromines on the less substituted carbon. Again, this is an anti-Markovnikov's addition. Now, if the alkyne is internal, meaning it's not terminal, then we can't really follow Markovnikov's rule. So if we have this alkyne here and add HX, we'll get hydrogen on one side, halogen on the other. And as I said, we will probably end up with a mixture of cis and trans isomers. In this case, it doesn't really matter because this was a symmetrical alkyne. So it didn't matter which carbon got the hydrogen and which carbon got the halogen. Where it does matter is if it's not a symmetrical alkyne. So in this case, what I mean by symmetry is it's the same group on both sides. So here, this alkyne has a methyl on one side and ethyl on the other. In this case, we're going to end up with a mixture of constitutional isomers. It's not necessarily 50-50. Don't think of it like that. We don't really know what the mixture is going to be until we do the reaction in lab. But the important thing to note is that in some of the product, the X will go here, and in some of the product, it will go here on that second carbon. And we generally, as chemists, we don't like this. So we don't really attempt, or we don't really do these reactions unless we're just trying to illustrate that we do get a mixture of isomers. If it comes to synthesis, we don't like doing stuff like this because it cuts down on our yields. We're not getting mostly of one product. We're getting a mixture of more than one product, and that takes more time and effort to purify, and we end up with a lot less yield. So you probably will not see me putting questions like this on an exam because it's not something we would really do in lab. Now let's take a look at another analogous reaction and the addition of a halogen. So if we add 1 mole of bromine or one equivalent, just like we saw in chapter or in our last unit, we will add that bromine in an anti-fashion to adjacent carbons. Now, if we use an excess, it will continue to react, and each carbon will end up with 2 bromines. It'll get rid of that last pi bond. So again, this is a reaction that's regulated by stoichiometry. Okay, so you will see on the exam or on your homework if it says excess, sometimes I get lazy and just put X and S. Then you assume you add enough stuff until all the pi bonds are gone. Now, one other sort of similar reaction that we'll look at is ozonolysis. Now, if we're starting with an alkyne, we're going to end up with carboxylic acids. So I'm going to highlight those 2 carbons and those 2 carbons for illustration. We'll end up with 2 carboxylic acids. And yeah, these are the same exact product, but I just want to show you that where all the carbons are going. Because if it wasn't symmetrical, let's say, for example, we did this. Then we would have this 3-carbon carboxylic acid from these 3 carbons. And we would have this 2-carbon carboxylic acid from these 2 carbons. Now, if it's a terminal alkyne, we still end up with 1 carboxylic acid as a product, but we get carbon dioxide as the other product. And here's where all this is coming from. So I'm going to highlight these 2 carbons, and then I'm going to highlight this one here. So we'll get a carboxylic acid, and that's where these 2 carbons are coming from. That last carbon forms carbon dioxide. So again, that's if we have a terminal alkyne. Now, in our final video, we're going to look at, again, a couple of analogous reactions where we're going to the addition of water across a triple bond, either a Markovnikov's addition or an anti-Markovnikov's addition. And you'll see that there will be some striking similarities between that and what we did in our previous unit.